All right, we're going to continue with mathematical induction, except our first example, we worked a question involving a series, a sum of terms. The questions I'm going to work now involve a sequence. All right, but before I get to the questions, I just want to quickly talk about a sequence again. Now, a sequence can be given with the terms listed, like this one, 2, 4, 6, 8, 10. And also, a sequence can be written in terms of a formula. So, for example, AN equals 2N, which means, for example, if I'm asked to list the terms, A1 would be 2 times 1, which is 2. A2, the second term, would be 2 2s 4. A3 would be 2, 3, 6, and so on, which describes this sequence, right? So this would be the formula for this sequence. But apart from a formula, a sequence can also be defined in terms of what we call a recurrence relation. A recurrence, I'm going to write it, a recurrence relation. Now, this way means the sequence is defined, or each term is found based on the term before it. So, for this particular example, for instance, AN, if I write it as a recurrence relation, would be equal to AN minus 1 plus 2. Now, what is this saying? This is saying for each term, it is equal to the term before it, because AN minus 1 would be the term before the AN term. So, for example, if we're talking about A7, this would be A6, right? So, this is saying AN, so any term, is equal to the term before it plus 2. The term before it plus 2. So, for example, A5 would be equal to A4 plus 2. So, A5, which in this example is 10, right? How is it found? It's equal to A4, the fourth term, plus 2, which gives us 10. 8 plus 2 gives you 10, right? So, this is the way, or one of the ways it could be defined. And in that case, it's called a recurrence relation, where each term is found by using the previous term, or maybe the previous two terms, right? It depends on the question. Now, one thing, they have to give you at least the first term. They have to start you off. You have to start from somewhere, right? So the first term isn't generated from a formula. It's given, and then you can use it now to find A2, A3, A4, and so on. All right? So that's how we can define a sequence, either as a formula, which is based on its position. So the first position, n is 1, so 2 1s 2. And then the second position, n is 2, 2 2s 4, and so on. Or a recurrence relation where we base each term on the previous term or terms. So just bear that in mind. This is one of the mathematical induction questions that I'm going to be working. The one we worked before was for a series. This one is for a sequence. So it says a sequence is given as, and they give us a formula, well, a recurrence relation for the sequence. Notice un plus 1 is equal to 3un plus 4, right? So notice each term is equal to 3 times the term before it plus 4. And they also gave us u1 equals 1. They started it off for us. By the way, this is not u, it's really mu, but I'm going to say u, right? For n being an element of the natural numbers. Using that now, we're to prove by mathematical induction that un is equal to 3 to the n take away 2. We're going to approach this question just like we did the one for a series. Remember, it's mathematical induction, so we're looking for 3 things, 3 steps per se. So the first thing, though, I always tell you to do or encourage you to do is to define what it is you're proving. Give it a name. I'm going to call it Pn. So Pn will represent the statement that I'm proving. And this is very important because when students are given these 2 things, sometimes they get mixed up and think they're proving this one, which is just the definition for the sequence, right? So you have to be careful. It says prove. So this piece is what I'm proving. So this is going to be my Pn. So my Pn represents mu or un equals 3 to the n take away 2. That is ultimately what I'm proving. Now we start just like we did in the previous one. We start with a base step. So I'm going to start with my base step. And remember, my base step is proving that the statement is true for the smallest value of n. So we're going to prove the statement is true for the smallest value of n. In this case, the smallest value of n is 1 because it told us n is an element of the natural numbers and the natural numbers start at 1. So we're proving that P1 is true. All right. So let's take the left side, right side, because we're dealing with an equation, this one. So the left side of that equation would be U1, right? The subscript is 1. You're proving the statement is true when n is 1. So U1 or mu1. And what is mu1? Well, it's given in the question. Remember, a recurrence relation, they have to give you the very first term at least. So this is going to be 1, right? And I'm going to make a note, given in question. Right, so the left side of this statement with n plugged in as 1, mu1 is equal to 1 based on how it's defined. For the right side now, I'm going to plug 1 here. So this is 3 to the 1 take away 2, which is 1. And we get the same thing on the right side as we got on the left. So this is equal to the left-hand side, which means P1 is true. Good. And we've done our base step. Now we're going to do our inductive hypothesis. Which is about assuming that your statement is true when n equals k. So no longer the smallest value of n, just an arbitrary value for n. So we're assuming that pk is true. And we're going to write it down mathematically. So we're going to say that is, go back to your statement, change the n's to k's. So we're assuming that mu k is equal to 3 to the k minus 2. That is our assumption. And remember, in the third part now, we must be using our assumption. If we get to a point and we realize we're stuck, always check to see, did you use your assumption? Right? So that was step 2. Step 3 now, I'm going to actually move to another slide. This step I call the inductive step. And in this step, I am proving that pk plus 1 is true. So the value after pk or after k is k plus 1. So our assumption is based on n equals k, which means the inductive step now is based on n equals k plus 1. So we're going to prove, I'm going to write it down mathematically. We're going to be proving that, let's go back to the statement, that mu k plus 1, remember we're replacing n now with k plus 1. So mu k plus 1 is equal to, let's go back, 3 to the k plus 1 minus 2. All right, that is what we're proving. That is what we're going to try to get to. Remember, I emphasized in the last class that just because you write it down doesn't mean you have proved it. Right? We actually need to go and do this proof now. So we're going to take the left side, which is mu k plus 1. We're going to write it based on its definition. So we have to go back to the question. The way it's defined, mu n plus 1 is equal to 3 mu n plus 4. So a term is equal to 3 times the term before it plus 4. So we're going to have 3 times the term before it plus 4. So 3, so mu k plus 1 is equal to 3 mu k plus 4. Good? And that's, let me make a note from definition, just to remind you. Then we're going to be using our assumption. Remember, our assumption contains mu k. So let's look back at what mu k is assumed. Well, rather, what mu k is, right? 3 to the k minus 2. So this is 3 times 3 to the k minus 2. So I'm replacing mu k with 3 to the k minus 2. Because I assumed in my second step that mu k equals 3 to the k minus 2 is true. So we're going to be taking that, plugging it there. And remember, 3 written as just 3 means 3 to the 1. So this is 3 to the 1 times 3 to the k when we distribute. Minus 3 times 2, that's 6. Plus that 4. Same base, we add the powers. And we end up with exactly what we wanted to end up with. 3 to the k plus 1 minus 2. So this is equal to the right-hand side. And then don't forget your statements. Therefore, pk plus 1 is true. Since, number 1, p1 is true, and number 2, pk plus 1 is true, assuming pk is true, then by mathematical induction, Pn is true. Remember, we did all 3 steps in order to prove by mathematical induction that Pn is true. Let me just remind you here that this came from our assumption.